Hello and welcome to the lecture 6, module 6, part A. The title of this lecture is Computer Vision through Machine Learning. In this lecture, we are going to discuss what do you mean by computer vision. Then we find out what are the major application areas of computer vision and what are the main challenges we faced during this computer vision algorithms. Then we going to discuss the conventional machine learning approach to solve these computer vision problems, and then we try to understand what are the limitations of the conventional machine learning approaches, and we introduce the deep learning approaches for this computer vision task. Then finally we discuss the different computer vision tasks and application by virtue of these deep learning models. So in this lecture, we start with computer vision. So first of all, we try to understand what do we mean by computer vision. Now in this figure, we can get an idea that when a human see an image, let's say this is the image, that through human eye, human or we can see this image. The question is how we interpret this image. So what is our interpretation of our human brain for this image? If you see this image, you can see very in object level understanding. This is a bird, then there is a clouds, then this is a blue sky, green land, and these objects are there. Now if you go a bit abstract level, we can say that this is a sign of peace, something, this white pigeon. Now the question is, this is a human interpretation. Now if we try to do the similar kind of interpretation of an image for a machine, then that we have to learn, or the machine should learn how to interpret. So ultimately it is a human-like interpretation through machine for a particular kind of scene or an image or video or anything input kind of thing. And the computer vision is basically that a robot or a machine can see through a camera like or a camera like sensor and then interpret some sort of similar object level or context level or more abstract level understanding. So this is somewhat this the computer vision. And by virtue of our machine learning or a deep learning kind of thing, machine can learn how to do this computer vision. Okay. So this is just a very overview of computer vision, a very brief or naive understanding of computer vision. Now it's a very interesting phrase that every picture tells a story. Now nobody is to explain what is the image of this. Okay. Now what is the goal of computer vision? Is to write a computer programs that interpret an image like this or any images. That we have to write the computer program. That is the main goal of computer vision. So our job in this twofold. First of all, understand what is the computer vision, what are the definition, what are the challenges of writing these computer vision programs, and then how to write a machine learning or deep learning algorithms so that a machine can learn how to do this interpretation of images, videos, any input model it is concerned. Since it's a vision, this we generally restrict on visual inputs. Okay. Now, what are the basic application areas of? There is a plenty of applications in computer vision nowadays. You can say that it's weather forecast. It's basically remote sensing applications on these satellite images. Other things can be used. Agriculture. This is still in agriculture also some remote sensing or drone imagery is used. Some insurance kind of thing. Manufacturing, underwater vision. This is a lot of things is nowadays going on. That underwater the challenge is very high because of the in underwater the image quality is very bad or very noisy. So how to enhance the image quality and try to understand the meaning of the images or what are the task of basic computer vision task can be done. Now from healthcare, now medical imaging is basically is one of the major aspect nowadays. A lot of work is going on in healthcare sector, banking, automotive, sports. Now sports is also a very big area of research at this moment, and definitely the surveillance kind of thing. So what we can see that there is a lot of application involved in computer vision. These are few examples, maybe others, lot of other applications also. And for this computer vision, this machine learning or deep learning algorithms are very important. Mainly the neural networks are very important tools or kind of research in this computer vision domain. Okay, now first we have to understand what are the main challenges in computer vision programs. Okay, so here we list some of the main challenges like viewpoint variation, scale variation, deformation, occlusion, illumination conditions, background clutter, interclass variation, etc. So here we discuss some of them so that to understand how we have to write the program, or in the broader sense how we make a neural net models, maybe machine learning, deep learning models for this kind of computer vision programs to handle these challenges. So first of all, the viewpoint variation. Now let's say we have to detect an object. Let's say that there is a car like this. Now it is possible that image is taken in a different viewpoint of this. Like here you can see the different car images, since the images are taken from the different view. So the idea is that if we have given this kind of images or this kind of object, can we learn our model so that even giving a different kind of views of a same object, it can detect as a the same class. So if you say the question, if a particular this image is given, now can if we just put it in a different direction, can your model detect it or classify it properly. So this is that particular image. Or if it is taken from some back side, can it be possible for them? So this is the one of the challenge, that if viewpoint has been changed, can your model still able to detect the object? Okay. The next challenge is the scale variation. Now you will see, if your particular model is being trained on the smaller cards, if the image is becoming, or the size of the image become large, can it possible for the model to again the classify properly? So visual classes often exhibit variation in their size, such this. Okay, so this is the another very important challenge. Okay, we'll see later how this challenge is being taken care of. Okay. Our next challenge is that occlusion, and this is a very important challenge. Now we can see here, this is a face detection algorithm, and now there is some object has basically occlude or cover some portion of the face. So face is our object of interest, and now another object here in this paper is basically that occluded or cover a portion of the face, a substantial, but it is more than half. Now the question is, if this is the situations, now can your model still able to recognize this face? Or here you can say this is the hand. This is a very frequent occasion where hands is coming here. So in this case also, can your model, can our model still track, or still you can detect the object or face, or you can recognize the face? Okay, so this is called occlusion. So some is visually blocked by other objects. So that is a very important challenge. So we have to take this into consideration. Our next challenge is illumination condition. Now you can see these images are the same image, but it is taken in a different lighting condition. This is a good amount of light, but if you go in right hand side, the light is being reduced, or it is possible that the light source is coming from the different directions. Okay, the question is that if this change is lighting condition, can our model can still able to detect or classify these images or recognize these images with the same accuracy? So it's challenging to take the same object in different lighting conditions. So this is a very important question in computer vision. We have to understand how to handle this kind of illumination condition, change illumination condition or changed lighting condition, how we handle this object detection kind of problem or other computer vision task. That is another very important aspect. Now you see the object of interest. Now these kind of wolf kind things are very much invisible even with our human eye in this background scene or background object. That they are basically the skin colors or the textures are very much resembles with this background. So if the foreground objects like these wolves interest may be mixed up with the background object, is called the background clutter, and is one of the most challenging can say problem in the computer vision. We have to know how to handle this situation. And finally, another very important thing, intra-class variation. Within a class, is all are basically dogs. So these dogs are kind of Eskimo, Husky and so on. They are substantially different. These dogs, they are all are dogs, but intra-class variation is very high. So it is tough to understand for a classifier that each these images are coming from the same class dog, rather than this crow, raven, this jackdaw, this kind of, these are the all the crow like birds. They should be coming under crow class, but this, if you see just it closely, then there is a substantial difference between these birds. So the interclass variation is another major challenge of computer vision algorithm. Specifically, we will basically learn a classifier for object detection and other type of tasks. Now we are going to understand how these machine learning methods are going to implement different computer vision tasks. So the basic pipeline of the conventional machine learning algorithms is like that. That is the input, that is a raw image. Now there is a feature extraction. So this feature extraction for conventional machine learning is by human intervention. So we as a human that extract features is sometimes called feature engineering. So this feature may be some statistical features, some patches, some geometrical features and so on. And when it is been done, that these kind of meaningful patterns, like we can use some SIFT algorithms, HOG, color histograms, like these are the kind of very well-known features. And after extracting these features, okay, and these features are fed to the neural network. Now the question is that how these features are look like. It's basically a kind of vectors. So this called feature vector, convert this feature to the corresponding feature vectors. So it's a fixed length numerical representation. Okay. So this feature extraction, the part, there is a, you can say there is a two kind of part, that is you find the meaningful patterns using this kind of algorithms, and then is converted into the numerical representation called feature vector. And these vectors are fed to the neural nets. Now the conventional case, these models are basically the shallow net. Okay, so it may be support vector machine, random forest, or it may be neural net, whatever, and then we predict or infer from this that okay, this is the what is the object, what is the image classification or object detection, whatever. But so these are the classic machine learning pipeline for doing the vision task. Now, what is the major limitation of this conventional approach? So first of all, that this kind of conventional approach could not handle the complex shapes or patterns, because that this generally they use the Salvan net. So what do we mean by Salvan net? Number of hidden layers is not that much high, maybe 1, 2, 3, something like that. Okay. Now the question is that if this is a very shallow net, number of hidden layers is very less, that we understand from our previous discussion that this kind of network are not able to model a very abstract level of understanding of from image or this kind of video, kind of any visual model it is. So they could not handle the complex shapes or patterns, or they cannot understand this abstract meaning of it. And this feature engineering is labor intensive. There is a lot of human potential is required for this. Now still it is a human design, so we cannot go for a very large amount of data. So the human, since the human is basically doing this feature engineering, we maybe can 10,000, 20,000, but we cannot say, we can say for 20 lakhs or 40 lakhs or 200 lakhs or some millions of data we cannot handle. So similar, we cannot handle the big data set, and there is some human mistakes may be possible. So these are the major drawbacks of the conventional machine learning approach. Now come that what is the deep learning. As we know that in deep learning, this feature engineering and this classification are somewhat clubbed. So we actually use a bigger network where number of hidden layers is very high, maybe 20, 30, even 50 and more than that also. So this thing, they can do the automatic feature extraction. So there is no human is involved for this kind of feature extraction. Okay. So since it is a machine, so then it handles the big databases. Okay. So first thing that deep learning can do, it handles the big data and it is automatic feature extraction. So there is the human error is involved here. So and again, since the hidden layer is very high number of hidden layers between these input output layer, it can handle very complex pattern or very abstract meaning of this, and it is highly scalable and adaptable also. Because of that, it is a kind of end-to-end kind of thing. So it is highly scalable kind of architecture. So this is the major advantage of deep learning for the vision applications. Okay. Now, if we summarize that what are the deep learning properties, or what is the properties of the deep learning when it is basically used for the vision application. So first we can say it's a negative point kind of. We need a huge annotated data, and annotation in any case is very costly, but it is required for the supervised deep learning models. There is a kind of trade-off. You can say that supervised deep learning models are very much accurate, but it's required the annotated data and huge amount of annotated data, which is costly. This trade-off is there. Okay. So you can say that the supervised DL models and deep learning models are very accurate out from conventional most of the vision applications. So that is the advantage, but we have to give the cost. And another thing, for deep learning algorithms, you require high-end GPU. So hardware resources is required. Okay. So this is also a bit costly, but again, from the performance viewpoint, it is very, very accurate. And another that we have also discussed earlier, that a different kind of training algorithm is required to train our deeper architecture. That thing what we have discussed is layer wise pre-training, that we have seen how we can use autoencoder kind of concept and layer by layer confine it. So these are the major aspects that we have to keep in mind when we use these deep learning algorithms for vision applications. Now we are going to understand some computer vision task and application using deep learning models. For example, here we just consider few of them. We start with image classification, object detection, semantic segmentation, pose estimation, depth estimation, optical flow, 3D reconstruction, image super resolution, denoising, deblurring kind of thing, action recognition, object tracking in video, medical image analysis, remote sensing, and so on. So some of them we'll discuss here, and in this course also some of the application will go in details. So let us start with a very brief discussion that how these applications or this computer vision task, sometimes it's called downstream task, also can be implemented using deep learning algorithms. So let's start with image classification. First of all, we understand what is image classification. In general, what we have understood that in image classification is try to understand what is this. This is a kind of dog image. So you can see that at the output the dog is 95%. So we have to design a classifier or a deep classifier for our concern, so that it can say that this is image of dog rather say cow, cat or other horse kind of thing. So here is a the image of cow of, and these are not this. So 97% of confidence it can say that this. So this problem is called image classification. Now nowadays there is a lot of models. First of all, can start with the CNN kind of thing, the convolutional neural network. Then come some more large or deeper CNN architecture like ResNet kind of thing coming into the, and then we'll see some nowadays transformer based models kind of thing is also is used this kind of problems for more, you can say for some more accuracy or something kind of this. So the basic thing is that we'll see this particular problem, that what we are going to understand, that what kind of model is more suited. Sometimes it is the ResNet CNN is more suited of this kind of image classification kind of algorithms. So next thing is semantic segmentation. Semantic segmentation means what? Is basically you can see that in a image, these are basically, these are the pixels actually. So semantic segmentation means we classify the each pixels. Okay, you can see that particular image this. So the pixels of a particular object is bit coherent. If you assume this and say this is the cat kind of object, but essentially we classify the pixels here, that is it is a sky kind of thing, so that it is a sky. So this kind of in this particular image, this is a cow. So and this for this pixel, these pixels are basically going to given this some homogeneity is there. So that's why it is kind of. So this is the trees, this is the basically land kind of thing, and these are the sky part. So kind of this pixel level segmentation is basically done by the semantic segmentation, and it is also been very much useful in this kind of object, because we assume that in a pixel from a object is more closely packed, or you can say there is a more kind of homogeneity among the pixels. So from that point of view, you can say there is some object level kind of segmentation algorithms there. Okay, so here we use kind of CNN, ResNet and other nowadays transformer level approaches are there. Okay, next is coming the object detection. Now the object detection things, this conventional object detection kind of thing is basically that use these features HOG, saved CNN. So these features are kind of used for the conventional machine learning thing. But first of all, we have to understand what actually the object detection means. There is a two kind of information we have to extract. One is classification, what is this, okay, and the where is this. So the localization and classification. So here you can say this particular is a kite, and 0.8 when it is a 0 to 1 scale. So it is a very high confidence, we can say this is a kite. So this is called classification. And another thing, this is a bounding box is given. So this bounding box is said that where this kite is located in the image. So here, so for that reason, that the sliding window, selective search, region proposal kind of thing algorithms are basically used for looking for possible regions with objects, where the actually objects or possible region of the objects actually lies within this image. Okay, so this object detection is another important algorithms in this computer vision task, and a lot of very good CNN kind of models and resonate and other transformer models nowadays is basically used for this object detection. Next come another very important thing, it's called pose estimation. So pose estimation is what? It basically estimating the position and orientation of a 3D space. You can see that basically position and orientation of a human object here. So object in a 3D space. So basically what we are going to understand in pose estimation is that we estimating the position and orientation of an object but in a 3D space kind of thing. So it is a lot of application in robotics, augmented reality, ICI means human computer interaction kind of thing. Okay, so here you can say this is a human pose they are estimated. So different techniques are used, model based technique, feature based, direct, hybrid, and definitely some deep learning based methods is basically involved here. Okay, next coming the depth estimation. This is also a very important computer vision task. Depth estimation is basically that finds a distance or depth information for each pixel or object in a scene or from this camera viewpoint. Now camera means what? Using one or more 2D images, enabling an understanding of 3D scenes from scenes 3D structure. So that if you say that from this here and this camera is here and the distance from the pixels from this camera is basically giving this the depth information. You can say the higher the distance, the blacker the image or the more, and lower the distance is the more, you can say non or more white is in or not rising some these colors. So that is the called the depth estimation, or where we find the depth. Okay, so this black region is more depth, you can see here, and these are the where it is the very close to the camera kind of thing. When your car is moving or something, there is a more reddish or kind of yellowish, that means it is close to the camera. So application involves robotics, augmented reality, virtual reality, autonomous driving, something. So these are the applications of the depth estimation, and this can be done in traditional method is stereo vision. If we have a two camera, we can find the depth. Another is the molecular depth learning, that given a single image, we have used a single image depth estimation using the deep learning things. In optical flow analysis, first you have to understand what do we mean by optical flow. So optical flow is the apparent motion of the brightness patterns, or you can say this object kind of, between the consecutive frames on the image sequence. So image sequence means you can say the video. Between two video frame, how an object is moving kind of. So what is the motion of an object between some successive or at least two frames in a video. So this is caused by a relative motion between camera and the scene. Okay, so sometimes camera is moving, sometimes scene is moving, and both are moving. So it's basically the relative motion. So basically it apparent motion, so it describes the apparent motion in the image. So may not be the true physical motion. That's why it is relative motion. Okay. So actually what it is, it computes the how the pixel intensities are changed across the frames or between two frames. So it describes sometimes object movement, camera movement, or both, if both are moving. So there is a lot of deep learning approaches find the optical flow. Next coming is very interesting. This is also, there is a lot of applications of there. It is a 3D reconstruction. So basically it is the process of generating a 3D object, three-dimensional structure or scene or object from one or two dimensional image. You can say that from the several kind of images we can find that this 3D object virtual. So kind of 3D virtualization kind of thing. So here we can estimate a depth analyzing the geometrical cues of the perspective, motion, disparity and shading kind of informations. Okay, so these cues are used to find the depth, and we have to find out what is the structure of this. These common approaches are kind of the stereo vision, structure from motion, multi-video stereo, and some learning methods, and very popularly known as neural radiance field. That is a deep learning method or model that basically do this 3D construction. There's a lot of applications. It's a very important thing, that robotics, autonomous driving, augmented virtual reality, culture, heritage, preservation, medical imaging, etc. Another very important aspect is image super resolution. Now, first to understand what do we mean by this kind of super resolution. Now, let's say you have a image, a small image. Let's say. So this is a good image, but if you want to resize it, make it bigger. Okay, so we zoom it to a bigger. So you can see there is some sort of some blocking artifacts kind of. So as a whole, what happened? We say the resolution is reduced. So resolution is basically measured by this PPI, the number of pixels displayed per square inch. So that things basically is reduced, because in normal resizing we use some kind of interpolation, kind of linear interpolation. So that's why the image quality has been degraded. It's become low resolution. Now the problem is, given a low resolution image, how can get is a high resolution image? So this is a resized image, the larger image, but in the same resolution. This is a one kind of way to understanding of this. Okay, so this is the called image super resolution. This is underwater super resolution. This is the 3x kind of super resolution. This is the some of the state of art result of here. Now there is a CNN based method, transformer based methods, diffusion based methods. There's a lot of other methods are available that these deep learning approaches have been used for this image super resolution. Next, coming the image denoising. Okay, you can say there's a lot of noise here. Okay, so we can say it's a frame by frame if you can say this particular video. So process of removing unwanted noise, this noise, and this is a clear image kind of. So we try to improve the clarity, sharpness and quality of the image for this particular video sequence or image sequence or particular image. So we can use a traditional filter based methods, that medial bilateral filtering, and some definitely deep learning based, where we are basically heading on this CNN based method, transformation, diffusion kind of methods that we'll need to discuss in details in the later part of this course. Another important aspect is called action recognition. Action recognition is basically that human action. We have to here in this example, it's a handshaking. Action is handshaking, and we are basically try to find out this. We recognize what they are doing here. So we automatically identify the human action using this these spatiotemporal patterns. Okay. Now, how we can do this? We can recognize in human action by capturing the spatial appearance. Definitely, we have some spatial information as the temporal motion information. What they are basically these humans are doing. Okay. So there is a lot of existing or kind of frequently used models, deep learning models for this particular task of action recognition, that is 3D convolution neural networks, two-stream networks, recurrent, that is RNN kind of transformers architectures are there. And it's a wide range of application like video surveillance, ACI, human computer interaction, this sports analytics, autonomous system, video content understanding, and so on. So action detection is one of the important vision task planning. Another very important thing is object detection. In better to say this object tracking in video. So object detection in video means we detect, not only detect the object, we track the object. Okay, so object aims to continuously locate and follow the object interest across consecutive frames of video. So you can say that this is a video, and we can this is a car kind of or vehicle. We basically track this. So the frequently used network is Siamese network, correlation filter based models with deep features, transformation approaches are basically very frequently used approaches. Okay. Now here what we are doing, we combine the spatial feature as well as temporal information, and these methods we use, it's very high accuracy. They got a very good performance, high accuracy. They can detect or like track this object in these video frames. And sometimes it is very much challenging, basically for like occlusion, scale variation, blurring, and illumination change kind of thing. This become a very challenging thing, but still at a very good accuracy of that. So object tracking is a fundamental component of applications such as video surveillance, kind of autonomous driving, robotics, sports analysis, human activity understanding, and so on. So these are the few application areas where object tracking video is very much used. Now next is the most important thing of computer vision is and you can say this is a kind of a big field of study. You can say nowadays it's medical image analysis. Now here we basically use the deep learning architecture for analyzing, interpreting, and extracting the clinically useful information from medical images. So that this particular image, there is a kind of pneumonia detection, right, kind of thing, deep learning based pneumonia detection from this chest X-ray kind of thing. So a lot of very popular deep learning networks are used. For example, you can say CNN models and ResNet, VGG Tensor for image analysis, while the UNet or fully convolutional networks kind of used for medical image segmentation kind of thing. Now there is some volumetric data, CT and MRI. These are the volumetric data kind of, and the 3D CNNs are used there. And we can use the transformer, high-bit CNN transformers are used for long-range dependencies, like for to captures for this kind of medical imaging. For example, vision transformer used there is very for this task. And autoencoder GANs, these are basically GANs is that kind of generative use for denoising, reconstruction, data augmentation is kind of generative thing. So these are the very well explored field, and a lot of research is still going on, and so that definitely we explain and discuss a lot in this course. Now another important aspect is remote sensing. Okay, so remote sensing is basically analyzing the data acquired from satellites, drones, or airborne sensor. So now this is basically that automatically extract the meaningful information from the Earth's surface. Just for example, if I consider this segmentation of these kind of areas. Okay, so what are the building pathways, what is the tree, and so on, these kind of things, rural areas, urban areas. So a lot of models, the convolutional neural networks, these recurrent networks like RNN and LSTM transformer used for process of high resolution optical imagery kind of thing. Then the multispectral and hyperspectral images, and this SAR data, this is called synthetic aperture radar. This is also very useful, that penetrate the cloud cover. This is satellite data, this penetrate cloud cover, and analyzing this we can get a very good information even in presence of the cloud. These methods are very much accurate, and they use for land use and land cover classification, semantic segmentation of the hyperspectral images, object detection, change detection, environmental monitoring. This. So there is a wide range of applications areas in agriculture, urban planning, disaster management, climate studies, and so on. So here we can understand that these are the data that have been analyzed using these deep learning architectures. So in summary, in this particular lecture, we define the computer vision and then try to understand the application and major challenges of computer vision. Then we understand what is the difference between conventional approach for computer vision and the deep learning approaches. And then lastly, we try to understand the different computer vision tasks, what are the different deep learning models that are going to help or that are going to used for doing this computer vision task. This is just a kind of a very brief overview, and some of the particular thing we going to in very details in this course. Okay, so in the next lecture we are going to discuss that how NLP, that natural language processing, using this machine learning,